All right, now this is the example that has the most oxygen in it, so we're never going to give you another one quite this complicated, but I wanted you to see this process and how it works when we do have oxygen all over the place. So we still need to figure out where our elements go, which ones are being oxidized and which ones are being reduced. So I'm starting by finding my oxidation numbers. If that's minus 10, this is plus 10, so that's plus 5, minus 4, plus 4, 0. Okay, so our carbon is going up from plus 2 to 4. So I think carbon's being oxidized, but always good to double check. Is I being reduced? Yes, it is. It is going down in oxidation number. Okay, so let's get that stuff separated out, and we're definitely going to want to do this kind of in the middle. All right, no charges on any of those things. Okay, so we have split our half reactions, and now we need to balance only our special elements. Our carbon is good, our I's are actually good as well. So we didn't need to balance those special elements. They were all good. The only things that were problems are our oxygens. So here we had 1 oxygen, and on this side we had 2. So we actually need to add 1 water molecule to this side. But we also have to do that in this reaction because our reduction half reaction has 5 oxygens on the reactant side and none on the product side. So we need to add 5 water molecules over here to get 5 oxygens. All right, and as soon as we choose to add any kind of oxygens or waters, we've got to balance those H's out that came with our oxygens. So because we added 2 H's to the reactant side there, we need to add 2 H pluses to the product side. Here we added 10 hydrogens, so we need to add 10 H pluses to this opposite side. And then it's electron time. And electrons are harder when we have all of this stuff with charges. But start by remembering which side your electrons are going to go on. It's always the product side of oxidation. And the total charge on this side needs to equal the total charge we already have on the opposite side, which is 0. And currently this product side where we're at only has 2 positive 1 H's, so we only need to put 2 electrons here in order to bring that down to 0. Now our reduction half, we need to put our electrons on the reactant side, and we're trying to get our total charge to match the product side that we already have, which is 0. And yet on this side we have 10 H pluses, so I have a positive 10 charge, which means we need 10 electrons here in order to balance this one out. And exactly like before, if our electrons aren't equal, which they definitely aren't, we need to make them equal. And the easiest way to make 10 and 2 equal is to turn that 2 into 10. So we're going to be multiplying this whole reaction and every substance in it by 5, which means we're going to have 10 H pluses and 10 electrons here. And as always, those 10 electrons are going to cancel out with these 10 electrons on the opposite side. But because of how we did this, and we added some waters and H pluses to each of these reactions, notice how they're also equal on opposite sides as well. So those H pluses and H2Os actually cancel each other out completely. And all that we're left with for our final overall is 5 COs plus 1 I2O5, making 5 CO2s plus I2. So the process that we went through with these half reactions separate was way complicated, but honestly this final reaction looks a little less complicated than the last one. We didn't actually need those H pluses and H2Os, which as a chemist tells me this solution or this reaction could be done outside of an acidified solution. We don't need the acid and the water in order to make this happen like we did in the last one.